Alright, well I just wanted to make a little video here and show you some proofs of Cartesian products. So we'll get started. We'll get started here on these two, and then I'll just talk just a minute about topology, just to try to give you a better sense of what that's about. Anyway, so we have ABC sets, and these are two properties of the Cartesian product, namely that the Cartesian product of an intersection with A is the Cartesian product of the one set intersected with the Cartesian product of the other set, which is intersected. And then this other property here, which is that the union of two Cartesian products is the Cartesian product of the unions of the sets, which would be forming the Cartesian product separately there. I don't have a good language for it, honestly, but you can see what it says. So to prove this set equality, I'm going to give us another example of a proof where I show that they have the same elements. I think that's manageable here, so let's do that. So I'll start by proving B by showing that these two sets have the same elements. So here's how that proof goes. I consider X as an element of the Cartesian product of A with the intersection of B and C. Okay, so what does that mean? That means that X is a pair, right? X1, X2 with X1 in A and with X2 in the intersection of B and C. All right, that's the first thing. Step 2. That is equivalent to saying that X1 is A, nothing happened there, right? But X2 is in B and X2 is in C, right? By definition of intersection. I suppose my proof could be improved a little bit if I actually put down by definition of intersection to go from there to there, but you'll forgive me. All right, so then I forgot what I was trying to prove, so I started trying to get to the other one. At this point, my eyes skipped, which is great. So I had to white out a couple steps right there. And anyway, we'll get to the next actual step. Oh, there it is. Yeah, you can't write with marker over whiteout. Yeah, just by the way, pro tip. Anyway, so X is an element of the. So we're going here from X1 is in A1, and X2 is in B, and X2 is in C to X, which is this pair, is in A cross B, and X1 comma X2 is in A cross C. That follows, this is interchangeable with that, right? Because to say that it's in the pair is to say respectively that this is in there and that is in there, right? And vice versa over here. X1 is in A and X2 is in B, but that's exactly what I have in the previous step. So I can go from here to here, or I can go from here to here. These are equivalent statements by definition of Cartesian product. So let's see here. So the next step is, okay, well that means that X is an element of A cross B intersected with A cross C, because X is in here and X is in there, right? So essentially to go from this step to this step, this is by definition of intersection. And consequently, we conclude that these two sets have the same elements and hence they're equal, all right? So there is a proof of part B of theorem 3.49 in my notes. And we'll do another proof or two of things involving Cartesian products next Tuesday, but you do have a homework problem on it, so I felt like I should give you, at least one example where I do it. So there it is. And sometimes proofs are great, but maybe an example with some sets in it is helpful as well. So if I have closed interval 1 to 3, the half open, half closed interval minus 1 to 2, and the closed interval from 1 to 3, the intersection of B and C is actually 1 to 2, if you think about it on the number line. And if we take the Cartesian product of 1 and 3, that's the green set. So this 1, 3 with 1, 2, that's the the green part. On the other hand, 1, 3, with minus 1 to 2, that's the blue set here, right? Over here, 1, 3 with 1, 3 is the red square. So the intersection of the blue rectangle and the red square is this little green rectangle, and that reflects, that's an example of the identity we just proved in general, all right? So there's one thing. Next up here, one more proof. Proof of E. Get down here. So E was a subset. E is a claim about subsets, right? So let me write down what E is again. So E was showing that A cross B, all right, unioned with C cross D is allegedly a subset of A union C. Sorry, I can't talk this morning. Cross B union D. All right, that's the claim. And let's see why that's true. So to prove a subset, we begin by picking an arbitrary element in the subset. So I start by reminding us that A, B, C, D are sets, and I let X be an element of this guy, all right? So then the next step, excuse me, is by definition of union to notice that X is an element of this, or X is an element of that, right? And I've circled this OR to help us connect logically with the next time I use that OR. All right, so hence by definition of Cartesian product, X is equal to X1, X2, where from here we have X1 is in A and X2 is in B. Or X is equal to X1, X2, where X1 is in C and X2 is in D. All right? Then we find X1 is in A or X1 is in C. And X2 is in B or X2 is in D. All right. So hence by definition of union, X1 is in the union of A and C, or X2, and rather not or, but and. The difference between and or is important. It's kind of like the whole, this is one of the things we have to get used to in Math 200 is being clear on the distinction between and or. In casual conversation, sometimes these words get, abused. People don't always speak as clearly as you might like, and sometimes that's the reason for interpersonal conflict. Anyway, so X1 is in A union C and X2 is in B in bud, and therefore the pair X1, X2 is in the Cartesian product of A union C and bud. So that proves then that X is of course an element of the Cartesian product of A union C and bud. I mean, this sentence here is unnecessary. My apologies. But anyway, thus by definition of subset, this set is a subset of that set because we proved an arbitrary element of here is necessarily in here, which proves it's a subset. All right. So it's almost never the case at this point. You need to be using properties of subsets we already have to prove things about subsets. It's almost always the case in this course that, at least at this juncture, you're probably going to be using the definition of subset to prove it's a subset. You're probably not going to be like combining propositions to prove other propositions. I mean, it's possible, but it's unlikely. All right, so that's that. Now, excuse me. Let me talk about topology just a bit. First of all, let me give a brief recap and in some sense restatement of the definition of topology. All right. So a topology for a set is a family of subsets such that the empty set and the whole set is an element of the topology. And if you have any collection of sets in the topology, then the union over that collection is again in the topology. And if you have any finite collection of sets in the topology, then the intersection, that finite intersection, is again in the topology. By definition, the sets which are in the topology are defined to be open sets. They're called open sets. And we say a set is closed if and only if its complement in S is open. All right, so this is the definition of topology. All right, and let's talk a little bit more about it here. So since the complement of the empty set, since the complement of everything is the empty set, and since the complement of the empty set is everything, we find that the whole set and the empty set are both open and closed because they have to be in the topology by assumption, right? By definition of topology, they're in the topology, and their complements are also in the topology, so they're sets which are both open and their complements are open, which means they're both open and closed. So open and closed are not mutually exclusive categories. You can have a set which is both open and closed. You can also have a set which is neither open and closed. That can also happen sometimes. So one of the things that, first things you learn about in topology, and I'm mostly just talking about it here because it gives us a good chance to kind of flex our set theory muscles, so to speak. Take our set theory out for a spin, I suppose you could say. A joyride, if you will. Anyway, so if you have arbitrary intersection of closed sets, it turns out they're closed. And the finite union of closed sets are closed. So I'll give you a little proof of the second assertion here. All right. Here's how that goes. So suppose we have closed sets C1 through Cn in a set S. All right. And I'm going to suppose a topology is given. All right. Then the complement of these sets S minus C1, S minus C2, S minus Cn, these are open sets by definition of closed, right? Which is to say, just to be more precise, that is C1 tilde, C2 tilde, Cn tilde, the complements of C1 through Cn respectively. These are open sets and hence they're elements of the topology, all right? Now, so then, that then follows by axiom 3 of the topology that the finite intersection of these open sets is open. But that means by remember, De Morgan's law extends to arbitrary unions and intersections. So it certainly goes for the finite intersection and union. So the finite intersection of the complements of Ci by De Morgan's law is the complement of the finite union of the uncomplemented set Ci, right? But what does this say? This says that the complement of the union is this set over here, which we already argued was open. Consequently, this set is closed because its complement is open. Right, so therefore, to conclude, the finite union of closed sets is closed as its complement is open, which is what I claimed up here in the blue. Right, now, I'm not going to give you the proof of the arbitrary intersection, but the proof is very similar to this. As you can imagine, you have to use an arbitrary collection as opposed to a finite collection. Now, I think you have the last homework problem you guys have is a much simpler version of this. I think I just did it for 2 sets rather than n sets, but if you can understand what I did here, that it shouldn't be too big a deal to do the last problem in the homework. And the larger point here is that your homework problems aren't really about understanding all of the nooks and crannies of topology or anything. They're really just about interacting with the definition of topology, which I've given you. All right. So abstraction is important, and the big part of abstraction is being given a definition, being able to work with it logically. However, in mathematics, we also like to gain intuition, so I figured I probably should say a little bit more about topology. the topology you most commonly run into in future math courses, maybe even currently a math course you're taking, is probably the Euclidean topology. So the Euclidean topology is the standard topology for Rn. It defines what's an open set in Rn. I'll show you the definition. This is not in the notes, but I figured you guys might be interested, so here it is. We say a subset, U is in the standard Euclidean topology, a subset of Rn. I should probably have said that. U is a subset of Rn. Let U be a subset of Rn. All right, there we go. I fixed it. So U is a subset of Rn. It's said to be in the Euclidean topology, the standard topology, if each point in U is interior. It's an interior point. Well, what's an interior point? Well, an interior point, P of a subset of Rn, is an element P in U. It's an element in the set, a point in the set for which there exists a delta greater than 0, such that the ball of radius delta centered at P, which is to say this, you're taking x in Rn, such that the distance from x to P is less than delta. All right. Oh, I never finished the thought. I guess I probably should. Oopsie. Subset of U. Oh man, that's what makes it interior point. If you can find an open ball around the point that's within the set in question, that makes it an interior point of the set in question. So here's some pictures of what open balls look like. So like these are also called the basic open sets of Rn. So in the plane, an open ball is just a disk, like a fuzzy disk with center P and radius delta, like that. In R3, I'll hazard a picture. An open ball is like a fuzzy ball, so the edge is fuzzy and the center is P. Here's my silly n-dimensional picture. Same idea. That was supposed to be a circle. I tried. Anyway, you notice here I can do this thing called shading, which is super awesome. Not possible on the whiteboard, sadly. Now here's a little bit more complicated example, and then I'll be done with this video. This is for your homework problem. The penultimate homework problem, I guess. If n equals 1, the distance from x to p is given by absolute value. So like you could do absolute value of p minus x or x minus p, depending on whether you're coming or going, I guess. Anyway, so the ball of radius delta centered at A in one dimension is simply the collection of real numbers such that absolute value of x minus a is less than delta. But if you work that out, that's the same as the interval that goes from a minus delta to a plus delta. Why? Well, because this inequality is equivalent to that inequality is equivalent to that inequality, which is, of course, to say that x is an element of a minus delta to a plus delta if x, has this condition. So we can write the ball of radius delta for the real numbers like this. And you should draw number lines and draw pictures. That's the way to solve that problem, by the way. So anyway, that's just trying to demystify that homework problem a little bit. It's still not easy. The last homework problem, I think, is way easier than the next to last homework problem, in my opinion. So here's my last spiel. Here's an example of a set in the plane. I wanted just to give you an example of 3 different kinds of points. I'll start with point 3, which is kind of silly. Point 3 is outside of the set. So if it's outside of the set, it's not an interior point. You might be like, well, wait a minute. It's kind of inside the set because it's inside where the shading was, but not in the shade. Well, no. Inside the set means it's actually an element of the set. That's not an element of the set. Now, P1, excuse me. P1 is an element of the set. And it's an interior point because I can fit this little delta ball around P1 and stay inside the set. This delta ball pictured here is a subset of this set, which I'm calling U. Here, U. There we go. Anyway, P2, on the other hand, is not an interior point because no matter what delta I choose, there's necessarily points outside of the set. I can't make a delta ball a subset of U here because there's necessarily points outside of the set. It's inescapable. And so what that all means is that U is not an open subset of the plane. I always tell students in less proofy courses that you should just think of an open set as a set which has fuzzy edges or no edges at all, and a closed set is one which has solid edges or no edges at all. Well, it has solid edges anyway. So final remark here. A topology for a set is a collection of subsets of S. What that means then is that the topology for S is itself a subset of the power set of S. Because remember, the power set of S is the collection of all subsets of S. So indeed, the choice of the topology of S equal to the power set of S is a topology that you can give. And you can check it satisfies all three axioms, all right? And if you do choose the topology of the set to be the power set, then that means that you're giving S the so-called discrete topology. So for a given subset, there are many different choices of topology. Topology is an additional structure. Declaring what open is an additional structure on the set, which is not, defined just by the set itself. So for example, if you take the real line and instead of giving it the standard Euclidean topology, you give it the so-called discrete topology, that makes every subset of R both open and closed. Because if you think about it, if you take a subset of R and you calculate its complement, it's still a subset of R, right? So if that's open, then that makes every subset closed because its complement is open. So anyway, there is just a brief a few comments about topology. We can talk a little bit more about it next class. This is not a class in topology, so we're just using this as an example, again, to explore set theory a little bit. And yeah, so that's where we are. And I think next week we're pretty much just trying to wrap up our ideas on set theory, and we've got a test sometime soon. I forget if it's next week or is it the week after. Well, anyway, you guys know it's all in the course planner. So thanks, guys. Have a good weekend.